Welcome, everyone. I'm Celia Merzbacher, Executive Director of the Quantum Economic Development Consortium, or QED-C. And we're excited today to have an episode of Quantum Marketplace, a program that QED-C does. It's very public facing. It aims to inform and raise awareness about quantum technologies in all kinds of areas and throughout the supply chain. But today we're going to be hearing about quantum sensors. And I'm very excited because of the panelists that we have and because quantum sensing is really, in some ways, the first area of technology application likely to be of really practical value, and in some cases, really already of practical and economic value. So thank you for joining us. Please share with others who are interested in quantum technologies about Quantum Marketplace and about QED-C. And with that, I will turn it over to our moderator and host today, Joe Christensen from SRI International. Joe, over to you.
Thanks, Celia. At the beginning, I want to thank everybody for joining us today. For our agenda, here's what we have lined up. I'm first going to give a quick intro to the quantum marketplace, then an overview of the types of quantum sensors that the industry has been interested in, followed by presentations from the QED-C member speakers, and then finally a panel discussion from the member speakers. So the quantum marketplace is all about giving QED-C members a stage to highlight what products or services they'll provide and connect with others. These sessions are recorded and shared on YouTube and the QED-C site, so you're welcome to type in questions at any point in the session through Zoom's question and answer feature, which you should see on your Zoom window, and the presenters will be able to provide text responses to the questions as they're able. And then finally, if you're a member company, make sure your online profile is up to date because it's a great way to get noticed on the QED-C site. This is a screenshot of QED-C's Quantum Marketplace webpage. You can access it via the link above or by clicking on the Quantum Marketplace tab at the top of QED-C's website. You'll see videos posted from past webinars, as well as profiles of QED-C members who provide quantum products or services. The QED-C also posts webinar and individual company videos on this Quantum Marketplace YouTube channel, which you can access through the link above. Next, I want to get into overview of quantum sensing. I don't want to take too long because I know everybody here is probably more interested in hearing from the panelists as opposed to me. So we're going to give a quick rundown of just an overview of quantum sensing. So quantum sensing, when we talk about it, is most generally the use of quantum phenomenon, so superposition, entanglement, wave properties, discrete states, to be able to measure some physical quantities with extreme precision. The types of measurements that we've seen already performed by quantum sensors include magnetic fields, electric fields, measuring time and frequency, acceleration, rotation, gravity, pressure, and temperature. Basically, all of the things that you could want to measure with a sensor, there generally is a quantum sensor that can often scale the sensitivity beyond the classical limit. And so why this matters is it does enable order of magnitude improvements for sensitivity or resolution or stability over classical sensors. Sometimes it can also allow for non-invasive or passive sensing where a classical probe fails. And it can really work in regimes inaccessible to classical sensors, such as on the nanoscale, where you could be using single atoms or single artificial atoms to detect magnetic fields. And some of the key quantum platforms include atomic clocks, which is really the most mature quantum sensor currently out there. It's the backbone of GPS and a variety of time sensors and standards across the world. You also have platforms such as atom interferometers, NV centers and diamond, superconducting circuits or squids, optically pumped magnetometers, trapped ions, and Rydberg atoms, which offer a variety of sensing from magnetic fields to electric fields to gravity, acceleration, and rotation. And some of the key application areas that quantum sensors have been looking into include navigation and timing, which is the backbone for GPS, Also, even geophysical and resource exploration, as you have gravity sensors or magnetic mapping to view what is underneath the ground. Applications have extended into medical and life sciences for brain imaging and nanoscale biosensing. A lot of these quantum sensors are also used for fundamental physics tests, such as tests for gravity or the precision of constants in terms of clocks. And these also have a lot of defense and security applications, including, just to name it two, submarine detection and underground structure sensing. In overview of the current state of the field, it is probably the most mature area of quantum technology that we've seen to date. There are a bunch of systems that are commercially available already for sensing. And really where the field stands today is it's moving from lab scale demonstration into field deployable and ruggedized devices. And so what we're seeing is the physics has been understood for a while, and now we are moving into engineering challenges of really being able to make these sensors useful in real world applications. With that, there are still a host of technical challenges, including maintaining these pristine quantum states in noisy real world environments and looking at trade-offs for sensitivity in size, weight, and power, as well as robustness. And in sort of more the economic side of it is the need for scalable manufacturing of these systems. As we're starting to get online with quantum sensors, we're realizing that there is a need for a supply chain behind it for all of the support devices in these systems. And there's also a limited availability of quantum trained engineers at the moment. That is my brief 5-minute overview of the quantum sensing landscape. And now I want to get into the meat of our discussion and talk to the panelists. So each of these panelists will share a short 5-minute presentation. And so these folks who we have with us today are going to share their perspectives on and experiences related to quantum sensing. And before we jump into the panelist discussions and questions, we'll hear a short presentation from each of them, and we'll start with William Clark from Infleqtion.
Thank you. I appreciate the opportunity to talk a little bit about what we are doing at Infleqtion. I'm Dr. William Clark. I'm the Vice President for Quantum Development. I've been with the company now for almost 4 years, and my job is really to help the company transition from where we started, which is really as a research as a service organization doing work with the DARPAs and the ARLs and AFRLs of the world, now to product development, where we're rapidly maturing these technologies into product lines that are beginning to transition into operational use. I will say that in 5 minutes I can't get into a lot of depth. I absolutely encourage those that are on to take a look at our website. There's a wealth of material there that goes into a much deeper level on each of the different products that I'm going to talk about today. So let me start with the history of our company. We've been around for a while. We're actually in our 19th year, so we're not quite a new start. We are about a little bit over 200 employees. A pretty high percentage of those employees today are PhD physicists and engineers, but where we're seeing most of the growth, again, driven by product development, is really on the engineering side. So all of the engineering disciplines, which are key and critical to designing, to fabricating, manufacturing, transitioning, and then maintaining these products over time, that's what's all coming into play today at Infleqtion. This all started back in the early 2000s. Dana Anderson, our founder, working with Nobel Prize winning physicists at CU Boulder and the General Quantum Institute, started the company. And the company initially was focused on advancing certain core component technologies, which are central to understanding the physics of things like Bose-Einstein condensates and room temperature atomic systems. That's where it started, and with the development of those kinds of cells, those various types of cell technologies and supporting systems. Over time, things have grown rather rapidly. I'd say in the last 5 years, we've seen this shift from doing basic research now into initial commercialization. This started with our optical atomic clock, which I'll show you in just a minute. And today, that is a product. It's available. It's in low rate production, and it is being transitioned into operational use. It's very exciting. But in addition to that, we've made some pretty significant advancements in our RF technology, which is based on rhythmic electrometry. That is now starting that PLC process and will soon be transitioning into operational use. And then similarly, there's been significant growth in or advancement in our cold matter atom-based interferometers, which are used for things like inertial sensing and gravity radiometry. And so this is us. So again, we're a quantum company, and the modality that we use across every single one of our products are atoms. And we use basically either the quantum electronic states of the atoms or the cold coherent states of atoms, or combinations of the both to create different types of products with different applications in mind. So as I said, we started with developing the core components, mostly in support of research and development at academic institutions and research labs around the world. Here's an example of one of these exquisite cells that we developed today. It is almost like a jewel if you look at it. There's atomics, micro-optics, electromagnetics that have all been integrated down into a small cell that you can hold in your hand. And with this, you can do some pretty extraordinary things with atoms. In particular, under our sensing business unit, you see here in the center, we've been able to use this core technology, the same atoms, the same kind of cells, the same kind of laser systems to build things like optical atomic clocks. Ticker is our first product in that category. It's roughly about 10,000 times more precise than the current chip scale atomic clock, 1,000 times more precise than the current cesium standard, and is being looked at seriously for GPS independent, ultra stable timing for precision navigation and timing customers. Skywire, that is our quantum RF receiver system. It's again a compact receiver, about 1 cubic centimeter in size, integrated atomics, micro-optics, and electromagnetic. So I was just wrapping up on Exact. That's our cold matter-based interferometer used for inertial sensing, gravity and gravity gradiometry. Lots of applications in oil, gas, mineral exploration, precision navigation, and so forth. We also have a couple other business units that aren't really relevant to today's discussion, but they are very interesting. Compute Scale is our neutral atom quantum processor. Today, it's one of the largest, if not the largest, neutral atom quantum processors in the world at 1,600 physical atoms or qubits. We have moved on to doing logical qubit processing. In fact, I think we may be the only company in the world today that's actually using logical qubits or error-corrected qubits to do computations. And we've demonstrated this recently at the quantum, at a variety of different conferences, including QTD and the World Quantum Congress, where we showed a 12-bit implementation of Shor's algorithm and its use to factor small numbers. And then over under the software business unit, it's started with our acquisition of SuperTech and SuperStack, which is a full development environment, allows you to develop it using high-level languages. And we do the hard work of translating those algorithms into quantum circuits and optimizing them for whatever the underlying hardware is, whether it's ours or somebody else's. And then we've made huge strides in now developing things like contextual machine learning, which is one of our quantum-inspired algorithms that is getting a lot of use today in a variety of different applications, including PNT, where we're using it to fuse multimode sensor data together to create better solutions, for position navigation and timing. We're also using it to improve the real-time performance in detecting and processing of RF signals. And in general, it really just opens up the context window in whatever degrees of freedom are available. So in time and space and in frequency to enhance the ability to detect correlations in all those domains and improve overall sensor performance. So with that, I will hand off the baton here to the next speaker.
Thanks, William. Svenja, if you would mind sharing your slides.
Thank you for having me. My name is Svenja Knappe, and I'm the CTO and one of the founders of Fieldline Medical, and also a research professor in the mechanical engineering department at the University of Colorado in Boulder. And I've spent the last 25 years of my career taking vapor cell-based quantum sensors and trying to engineer them so we can take them out of the lab and into application. And specifically, or one of the big applications I've been interested in was biomagnetic imaging, specifically brain or heart imaging. And we founded Fieldline Medical in 2017, really out of a market pull, which isn't always the case for quantum systems. And so the problem we're faced with when we think about brain disorders is that is a huge prevalence. 1 in 5 people has a diagnosable brain disorder, and that's scary. That's big. It's a big challenge for our society. The the global market is about $1 trillion US dollars. $1 trillion in the US, about 16 trillion globally. And if you look at and it's kind of hard to describe brain disorders in terms of economics, but if you look at these disorders, a lot of them are long-term disorders we have no treatment for and we don't understand really well. And so there's a very big need for better tools, specifically non-invasive tools to image for diagnostics, treatment monitoring, to aid therapies. So if we look at brain imaging modalities, here I put spatial resolution onto the vertical axis, temporal resolution on the horizontal. The workhorse we all know is MRI, magnetic resonance imaging, and it images water distribution. So it's not functional, but it tells us where is what. If we're interested in function, and if you look at these disorders, a lot of functional disorders, we need to look at functional methods. So there's functional MRI, which images oxygen distribution in the brain. Not quite the same resolution as MRI, but here we go. Then we have the radiotracer methods, such as positron emission tomography, where you inject a radiotracer into the body and you can image glucose or some of the proteins. If you're interested in direct electrophysiology, you have electroencephalography, where you glue electrodes to somebody's head. Very high temporal resolution, but very poor spatial resolution. You get a better spatial resolution with a magnetic counterpart, where you measure the magnetic fields coming out of the head. But if you want really, really good spatial and temporal resolution right now, the only option is invasive. You drill holes into the skull and you inject electrodes on the inside. And so one of the hopes we have for some of these quantum imaging we're building is to move this non-invasive magnetoencephalography into that range with very high spatial and temporal resolution to start challenging these resolutions we currently only give with invasive methods. So if we look at how a current magnetoencephalography system, MEG system, looks like, it's here on the left. The top left, you see it's a gigantic helium dewar, and on the bottom, liquid helium dewar. At the bottom are superconducting magnetometers embedded in this thing. You stick your head in there. You can see on the top left the photo of somebody's head in there, and you can measure the magnetic field that is naturally coming out of the heads when neurons fire on the inside, because the neural currents create a magnetic field, and your head is transparent to those fields and gets picked up by this array of sensors. If we can build quantum sensors that don't need that cooling, we can move these sensors directly to the scalp and create movable systems, but we also get very much closer to the source of those signals, and we get much higher signal amplitudes. And on the bottom, you see, for example, a brain response that we measured on the left with one of those squid-based systems, on the right with one of the quantum sensor-based systems, and they're on the same scale. So you can see much higher signal amplitudes, and it also results in higher SNR, even though our noise floors are still higher. And so the technology we have built is an OPM magnetometer, optically pumped magnetometer, based on laser spectroscopy in vapor cells. And we worked very much on translatable technologies. How can we make these technologies on wafer scale? How can we use these lasers that are telecom lasers for these? And so merging this MEMS technology with atomic spectroscopy is how we created these sensors. And on the right, you see the size. Each sensor is about the size of a AAA battery. The technology timeline has been very long. We made our first small sensors in 2004. And then we really spent 15 years. So the first brain signals we measured in 2009, 2010, and it took a very long time to convince a medical group to adopt a new type of technology. And so this is one of the challenges we face with these new technologies we develop. How do we convince the field of medical doctors that doesn't know anything about technology to adopt something they don't know? And so this has been a long path. We first developed this at NIST. Then I switched to the University of Colorado, and then in 2017 we founded Fieldline. We're by now on the third commercial device that we sell. We sold our first device in 2019, and we're currently going through FDA approval with this device. And so we had to learn how to scale, how to make a lot of these sensors, and actually how to deal with the user groups. Whoops, this doesn't look so good. This slide does not come out very well. I don't know where pictures went, but contact me if you have questions. Come join our team. We're hiring. We have about 40 installations of these brain systems around the world now. We have about 30 customers all over the world. And yeah, we make thousands of sensors in a year, and it's exciting technology. So I have.
Thank you very much, Svenja. Next, we will move on to Elizabeth Iwasawa from Leidos.
Hello, I'm Ben McDowell from Leidos, and I'm excited to be here today to share a bit of what we've been working on in the area of quantum sensing. Leidos is a technology company with extensive expertise in the areas of payload development, systems integration, software, AI, cybersecurity, and more. Our quantum technologies team works to develop near-term, fieldable quantum solutions that can help address problems faced by our defense, intelligence, and civil customers. To do this, we translate low TRL research from the lab into high TRL fieldable solutions with the help of our key academic and foundry partnerships. Given our focus on near-term fieldable solutions, we are specifically interested in devices that operate at room temperature, leverage at-scale CMOS fabrication capabilities, and are noise resilient with small form factors. Our team is relatively young at about 4 years old, and so it's been exciting to see how much our team and portfolio have grown over that time. Our portfolio covers technical areas across quantum photonics, sensing, communications, and post-quantum cryptography. And within this portfolio, we do a mix of internal research as well as customer-funded programs. Today, I'll be sharing a bit about what we're focusing on specifically in the area of quantum sensing. To achieve quantum sensors that are resilient and low swap, we see integrated photonics as a critical enabling technology. Some examples of these that we're working on are visible wavelength PDKs, nonlinear optics, frequency combs, and integration of chips with neutral atoms. These enable our quantum sensing solutions, where we are focused in RF sensing, magnetometry, gravimetry, and CBRN sensing. Today I'm going to give a bit of detail on two of our quantum sensing focus areas, which are magnetometry and gravimetry. For quantum gravimetry, we are developing a drone-based device for infrastructure assessment. This addresses key challenges with implications for public safety, where present inspection methods are expensive and provide an incomplete picture of infrastructure. Quantum gravimetry provides a path towards more frequent and more detailed inspections by enabling a holistic surface and subsurface picture of critical infrastructure. For our work in this area, we were excited to be selected as a winner of Stage 1 of the ARPA-I Ideas and Innovations Challenge. If you'd like to know more about this project, a summary of our work can be found on the Department of Transportation's website. In the area of quantum magnetometry, Leidos Defense Sector is working with the DIU to help develop navigational capabilities based on local variation in the Earth's magnetic field. This capability is enabled by the high sensitivity of quantum magnetometers and can be used to navigate without reliance on GPS signals. Leidos is working with quantum magnetometers developed by FEI and MIT Lincoln Labs to conduct test flights and demonstrate magnetic field-based navigational algorithms. Leidos' work in this area will be important for developing reliable sensors and algorithms for navigation in GPS-free environments. Thank you for listening. If you'd like to know more about our work or are interested in collaborating with us, please reach out. We'd love to hear from you.
Thank you very much, Elizabeth, for that wonderful talk. We will now move on to Nick Werstuck from QVIL, or Quantum Valley Ideas Lab.
Good morning, everyone. My name is Nick Werstiak, and I'm the CEO of Quantum Valley Ideas Lab based in Waterloo, Ontario, Canada. I've been here at QVIL for 5 years, driving our strategy and growth and taking our research into commercial markets. Today, I'll talk a bit about our approach to quantum sensing, applied research, development, and commercialization. But first, let me start by introducing everybody to QVIL. So we are an independent, not-for-profit industrial research lab, founded in 2018 and supported by Mike Lazaridis from BlackBerry Frame. And we're based here in the OG Quantum Valley in Waterloo, Ontario, Canada. So our mission is to accelerate development and commercialization of quantum technology. And we do this by identifying interesting ideas and investing in a 3 to 5 year project to take that idea to commercial ready prototype, and then creating spin-out companies to productize and commercialize. Along the way, we developed significant IP and have over 50 international patents filed and awarded over the last few years in atomic sensing. So we focus on application-driven research across a range of quantum sensing technology and have been recognized for our sensing work. That work has created our first spin-out company called Waveride Instruments that's commercializing that for spectrum intelligence and 5G telecom use cases. In terms of partnerships and support, we're supported by the Canadian federal and provincial governments here in a broad set of research contracts, many with DARPA in the US, as well as some Canadian entities with National Research Council, DRDC, and have been quite active in a NATO working group where we recently did some quantum enhanced radar field testing in the UK in the fall. So next, let me give you a view of our technology and use cases. So across the bottom, you'll see kind of the technology development that we focused on, and we've organized our teams into, I would say, delivering these key quantum sensing building blocks. Across the top, you can see how these building blocks come together in support of specific applications. So let me start with the technology first, right? So it starts with sensors and fabrication. There's some images of the ones that we've been fabricating here. We have significant IP and expertise to make high-quality atomic sensors, specifically Rydberg sensors, as well as others, and are ramping towards wafer-scale production. So you can see the small square sensors with some unique engineering, but also then some of the enhanced sensors to drive sensitivity with photonic crystal structures. For control systems, this is really the expertise in optics and spectroscopy. So putting together the lasers, control systems, and optical components to drive the sensors. Critical focus here, as others have mentioned, is on SWaP-C and capability to drive sensitivity and agility. For signal processing, these atomic sensors bring potentially new opportunities, right? We can leverage both the signal we're detecting, the classic RF signals, but we can also understand how the atoms respond to those signals and potentially enhance our detection. And then finally, part of our mission is to integrate these things into, as I said, commercial ready prototypes. So we pull together those components and delivering solutions, testing them here and then testing them in the field. If we then look at how those things come together, you can see the solutions across the top. So our startup, you'll see reference there, Waveride Instruments, is kind of taking the lead now on the use cases for 5G network testing, measurement, and operations, as well as the spectrum intelligence, electronic warfare use case using the initial technology we've developed. There's also exploration of using those sensors in space, and that is another area of keen interest, obviously, as people look at potential benefits. What we're working on really at QVIL is driving forward with the enhanced atomic sensor for multi-static quantum enhanced radar. And so that's really tied also to our development of an optical atomic clock and a timing synchronization capability. Final project is on a multi-axis NV diamond gyroscope accelerometer, and that's really, as others have mentioned, pursuing the benefits in GPS-denied navigation. So to make it kind of a sense of progress or reality, this picture represents the, oops, too fast. This picture represents the prototype, the product that our spin-out Waveride is now starting to deliver. You can see kind of the 25-liter package control system that has all the optics and the lasers and the FPGA systems for processing. And then up in front there is a very small sensor fabricated here in our labs in our facilities. It gives you a sense of we're definitely getting pushed more and more to drive towards more packaging, earlier testing, more field work, I think, as others on the panel have mentioned already. So the other sort of area of focus from a use case is to take these atomic sensors, enhance them for sensitivity to get below the thermal noise floor, and then package them up into this network of distributed low SWaP-C, low cost, but high performance sensors that can then function as a multi-static radar. So this ties together both those receiver sensors that we're developing as well as the atomic clock, right? And today we're working on the sort of the packaged prototype of a 2-node X-band system, right? And then the vision or the capability is really able to drive these towards multiple frequencies in the same package due to some of the natures of the atomic sensors. The picture on the bottom shows a view of our sensor packaged for some field testing in the outdoors that we did recently, as we start to think about how these new kinds of sensors would actually work in cold and harsh environments. Just to close off, right? Happy to connect after this webinar. Please don't hesitate to email me or find me on LinkedIn. From a QVO perspective, we're keen to engage ecosystem partners who might have products or use cases that could leverage our technology. We're also, I think as Celia mentioned, the supply chain is critical. So we're always looking for interesting supply chain partners with lasers, optics that can help drive SWaP-C and production volume of these systems. And finally, we are always looking for project ideas. And so we're interested in researchers who might have good ideas, who might want to see their idea cross that first valley of death, from idea to commercial ready prototype. And I'm happy to discuss if there's a project that we could do together at QVille to make that happen. We'll love to give people the chance to see their baby grow up and become something real. So thanks for your attention, and I will send that over back to the panel for discussion.
Thanks so much, Nick. And thanks for all the panelists for your presentations. At the end of this, I want to remind everybody that there is the Q&A feature at the bottom if you want to type in your questions to any of the panelists. And panelists, if you have time in between, feel free to type in your answers at the bottom for the little Q&A tab. Let me go back to sharing my screen. And so now we have to, after the presentation from all the panelists, we can move on to some of our panel discussion questions. So there will be four. We'll start with the first one, which is, where has quantum sensing clearly demonstrated an advantage over classical sensors, and where do you think that this advantage is still hypothetical? I will offer the panelists the chance to jump in if they have a start to the answer. Will, you've come off mute. I'm going to go with you first.
So I would say with quantum optical time, absolutely, right? I mean, although you could argue that microwave, atomic devices are still quantum devices as well. But yeah, if you look at what we're doing today with Ticker, we're literally 10,000 times more precise than current scale atomic clocks, and 1,000 times better than the current cesium standard. To me, that's a great example of the impact that we're having and how the needle is moving and demonstrating quantum advantage today just through the use of a clock. I will say that you can also use a clock in other ways. For example, you can use it as a frequency reference, right? As an oscillator, and that has exceptionally good close-in phase noise performance. And so that is being put to use today to make things like radars and comm systems better, more sensitive, less sensitive to phase noise. In the case of radar systems, absolutely reduces it improves your ability to reject clutter and detect slow-moving targets. So those are all good examples of how just one quantum technology today is having an impact in comms and sensing above and beyond where classical systems are, or I would say current state of the art is today.
Thanks, Will. Nick, would you like to?
Yeah, so I was going to parse this as well. I agree all with what Will's just said, right? I think there's lots there. I think let me parse the word advantage, because I think a lot of folks focus on pure sensitivity as the only advantage that they're going to get from these technologies. And I think, the question, part of the advantage answer is when these technologies and these new quantum sensing technologies may bring capabilities that you just can't do in classical domain. And I think, in the RF domain, the ability to create a sensor that'll work from hundreds of megahertz up to hundreds of terahertz in the same sensor and be tunable. You can call it a quantum antenna, you can call it a software-defined antenna, because you can drive it to those different frequencies with the laser control system. That's a really hard thing to do with classical technologies, right? And maybe with good sensitivity and additional flexibility, that may bring advantage to your use case that you can't get today. And so I think that's also a dimension that people can think about with the benefits of these quantum sensing technologies.
Yeah, that's a great point for new applications that we should see from these quantum sensors. Svenja, would you?
Yeah, I think The types of sensors that I usually work with aren't the best sensors. Like I worked in the chip skeleton clock, not the best clock out there. These OPMs we build, not the best magnetometer worldwide, or that's not our focus. Our focus is um, to make them as small as possible, as low power as possible. And so the advantage you get, for example, in the brain imaging, is that we can get closer to the brain so we can get more information. But the advantage that actually for a lot of people is equally important is that now instead of being stuck in a big system, it's a wearable technology. People can move around. They can now study interactions. They can measure kids. Children are incredibly hard to measure because they're just not going to be still in these machines and the interference is huge. So now you can start trying to understand the brain from much early on, working with infants, with young kids, kids with autism, things like that. That's just been traditionally really hard. So it's these, I would say, secondary advantages that we get. We're not making a better sensor, but we're bringing it closer. And the same with the chip scale atomic clock. It's not an incredibly good clock. And the advantage really for applications came because it was the first atomic clock that worked on a AA battery. So it opened up this whole new range of applications that just wouldn't use an atomic clock before because you had to plug it in. And so I think there's this whole slew of secondary advantages that are these quantum sensors can give us that are very important for the application base. But they're kind of hard to specify sometimes as a general. This is what quantum sensors give you.
I think that's a great point for maybe too much focus in the quantum sensing world on just sensitivity as opposed to all of the new features that you would actually get and things that people haven't thought of at the moment. Elizabeth?
So I'm going to play slightly the devil's advocate here on where is the advantage still hypothetical to sort of round out the conversation of it. Where I think is really interesting is we talk a lot of the time about the sensors themselves. And Sonia, you started to touch on the environments or the applications and use cases and the challenges of where they deploy them. If you go to any satellite provider or intelligence group and say, I can put this on a satellite, usually their first question is, what kind of lasers are you using? Because we have so focused on smaller sensors, more powerful sensors, and what people tend to forget are the 3 half racks next to it and the big honkin' power hungry laser that you have to drive some part of your system. So I think that's one of the places where I see the advantage as hypothetical is, we talk about moving out of the lab and making more robust sensors, but there's all these other pieces where the supply chain being critical. Is there someone who can make on-chip lasers or powerful lasers of the right swap to go in your deployment environment? Similarly, we discussed very briefly a MagNav opportunity that we're working on. And something interesting that comes up is, as far as advantages go, this vector magnetometry, you can't do it classically, so that's a great feature. But as far as sort of an advantage that it gives you, we don't have magnetic reference maps that are precise enough to use it. So we have this incredible sensor that allows you to navigate magnetically, but nothing to use to navigate with. So in some ways, that push towards sensitivity has actually moved beyond utility, and now we have to go make these incredibly sensitive magnetic maps to use it. So I think now that people are catching on to all the ways we can use them, there's these interesting questions of, do we have the resources to use them for infrastructure in the use case or on the platform? And I'll end that soapbox there. Thank you.
Thanks. Yeah, that's a great point for the hypothetical advantages. As we sort of said at the beginning, a lot of these things have gotten to the point where the physics is well understood and we've pushed it to a appreciable point. And now it is actually engineering challenges to be able to either shrink laser systems or move other components, not just the sensor head, into smaller packages to be able to field different possibilities from them. Those were all great answers. Thank you very much. I would point out in the question and answer section, we're starting to get a few more and also directed at some of the panelists. So if you have time, panelists, please feel free to look at the Q&A section and type in your answers. For the second question, I want to get everybody's opinion on where do you think quantum sensing is going in the next 5 to 10 years? So thinking about 2031 to 2036, where would we be for quantum sensing at that point? William, first off mute again. I'm going to come right back to you.
That's great. Well, so I agree with Elizabeth that there's lots to be done, to size systems down, reduce swap and pricing as well. Cost is key and critical here to be competitive in some cases. And so there's a lot of work going on. I think you've seen some in Svenja's slides. They had to go into wafer style kind of manufacturing of cells to make them smaller and improve the yield. On the cell manufacturing, that's a big deal. Similarly, the work that's going on with PIC, photonic integrated circuit implementations of things like lasers and frequency combs and all that. That's also key and critical, not only to reducing size, but improving performance, right? Making these systems more reliable and resilient, and to work in operationally relevant environments on platforms that shake and vibe and under pressure, over pressure, temperature variations, right? That helps to start addressing those kinds of real world operational needs. And then lastly, it's cost, right? The PIC integration is going to allow us to dramatically reduce the cost to make them much more less price sensitive compared to some of the existing technologies that are out there. And so that's what I expect to see, is that we're going to be adopting these next generation fabrication and manufacturing techniques, these new modalities for implementing things like lasers, going from diode based systems into PIC based systems. That is going to happen over the next 5 or 10 years, and it will usher in a whole slew of new types of sensor technologies that will absolutely start to not only replace sensors, but I think the second piece, and this is what panelists have also mentioned, it'll start to challenge the way we think about architecting solutions, right? When you think about all the new tools that are available that these quantum sensors have, all the new capabilities that are above and beyond what existing sensors do, coupled with the enhancements in sensitivity, the physical size reduction, you start to imagine ways of implementing solution problems in new ways, architecturally, right? And being able to put sensors now on the platforms that could never previously have supported those kinds of sensors, especially at low frequency. Nick was talking about HF and below is really hard to do on platforms, right? But that can be offered now because the sensors that Nick and folks are developing, as well as we're developing, we can put those on small drones, small UAVs, right? We can put them on small sat. That fundamentally changes what you do on platforms in all domains. So I'll stop there.
Yeah, I think that's a great point for considering also maybe how computers went from large mainframes to PCs and laptops and now opened up a whole host of applications beyond that. Elizabeth, would you like to chime in?
Yeah, I wanted to jump off because William mentioned PICs, and that's a huge focus area. So clearly I am in agreement with you that is a brilliant path forward, given on what we focus. But I think what you'll start to notice is, as well, in about 5 to 10 years, there will be key technologies and sensing modalities that survive, and they will probably be, in my biased opinion, right, sort of more PIC-friendly ones or more deployment-friendly types. Things that require giant cryostats are going to kind of fall more into the realm of academic research, and they'll be leading the edge of what we'll try to then deploy on these smaller platforms. I think you'll see sort of like people tout, we'll start picking 1 qubit eventually, TBD if that ever actually happens. But I think you'll see some of that in the sensing realm of these are actually deployable modalities and these aren't. There will be materials that we will stop using because we can't manufacture them in the United States with good quality. And I think I feel like I've become the boring supply chain person the longer I work in quantum, but it's a critical piece of our infrastructure. And if you can't manufacture it in a way that your customers are happy with, or you can't make good quality at home, or it's vulnerable to disruption externally, that's going to start becoming forcing functions that will drive the physics that we do. Also, I think we're going to start seeing them on platforms. We are going to start seeing them in the field. DARPA and its sort of compatriots in the research labs out of the military, they really focused on, can you make the next best sensor? Can you make the great sensitivity? And the current projects aren't like that. They are bidding programs where in 18 months, you have to have a sensor that you hand to some random person on a helicopter, and it has to be able to operate on the helicopter with zero interference from the creating team. They are no longer looking for cool sensors. They are looking for functional sensors. So a lot of the funding money towards the lower TRLs are pushing that forward. So I think not only will we see a sort of natural selection of what survives, you'll start seeing it in use in the field.
That's great. I mean, that's one of the things that, as two panelists have talked about, PIC integration. I know I've, in my own research, have been harping on that for a long time. And maybe the next question, along with the next to see in 5 and 10 years, do you think that PIC integration will happen in the next? That is a large engineering challenge, and people have talked about like putting lasers and gain material on PICs. Currently, that's maybe very expensive, or very few foundries are able to do that sort of heterogeneous integration. And maybe Nick, along with that question, I don't know if you want to pick up the PIC integration as well.
Yeah, sure. I was going to pile on again, William and Elizabeth's comments, right? So a lot of good comments about the building blocks improving there, fabrication of sensors, lasers, PICs. I think, if we're to declare some sort of victory in this space in the next 5 to 10 years, I think it does have to render into capabilities that become products that either defense or public safety or companies are going to buy and use, right? So I think that's got to be a real deliverable. And I agree 100% with this shift from experimental stuff to, like I call it, posting a number, like getting your technology to a point where it's packaged up, ready to go. You're testing it in the field and you're showing kind of the as is to be benefit of what the technologies can do relative to the application that people are considering for it. And so I think all that has to happen, right? By, hopefully sooner than 5 to 10 years, based upon all the effort that's going into these things. But I think it's critical that we deliver real, platform-based capabilities, real market products, real things that people can buy and that start to get broadly adopted or at least adopted in key use cases. On the PIC side, I agree 100%. Like, I think everybody probably on this call in sort of in this ecosystem is looking at how photonic integration can play a role in benefiting the stability and the performance and the swap size, of their solutions. And I think there's certain things that, we can all benefit from. I think as that community develops, right, clearly there's going to be a lot of crossover from the optical communications, optical switching, optical networking market that's going to happen if you believe all the projections there for all us to have these AI clusters that are going to scale to infinity and beyond. Then I think there's a benefit there for us to potentially leverage and ride some of those coattails. The challenge we have, I think, in quantum sensing is the uniqueness of all our solutions, the choice of the species, the choice of the wavelengths. It just complicates life and makes it harder. The choice of the PIC material, right? There's lots of innovation to be done there. I think that's all starting to happen, but I think rendering that into capability as a viable building block, I think there's still a lot of work to be done over the next 5 years to do that.
Thanks. That's great. Svenja, would you like to comment?
Well, I come from the side where we're now in the 3rd generation product. It is something we can already put in people's hands, even though it isn't clinical approved yet. There are already some quantum sensors out there, and we have this lofty goal to really democratize MEG and put this in, make this accessible for everybody, and not just maybe one center in each state or something like that. So that, of course, requires to scale. That requires making these robust enough and being able to scale up. But I think some of this sensor technologies are already there that we can. Some others we still need to develop. And so I think for a lot of these, we already have the right building blocks. And I think in 5 and 10 years, we will have these quantum sensors out there and people will be using them, and often they won't even know there's quantum inside, because the user really doesn't care if it's quantum or not. They care about what it brings to them. And I think in 10 years, I'm sure we have a whole slew of sensors that people use and are used, and nobody knows that it's quantum and or not.
Yeah, I mean, that would be a great, great way to get to in 5 and 10 years. And I think all of your answers to these questions will lead into the next panel discussion challenge, which is which technical challenges are we closest to overcoming? And I also want to get along with that, ask, as we've been talking about PIC integration and some of these other things, is this a technical challenge that the people fielding the quantum sensors should be working on, or is this something that like photonics foundries need to be working on, and really we're just waiting on somebody else to solve the problem? Will, you're first one off mute. We'll start with you.
So I think if you look at what's been demonstrated in the lab in a lot of cases, a lot of different sensing modalities, there's really good performance to be realized, right? Or has been realized. But getting that performance in a prototype or into an MVP, a product of some sort, right? That survives the environmental challenges, right? The shock, the vibration, the temperature variations, all those sorts of things. That's really the next big leap, right? And so everything that we've been talking about, just like you said, the integration in our case, like with the atomics, with the micro optics and electromagnetics, along with the PIC integration, that all results in an overall better system solution or product that is going to be more robust and reliable in those kinds of environments. And so those are things that we're absolutely working on, so that the product that we offer is really a product, right? Something that will have operational utility to it moving forward. So those, I think, are the closest things. The challenges we're working on now that we are going to be able to overcome here just in the near future. We've largely done that, I'd say, with Ticker, which is our first product out there, and there's more advancement coming. We're going to see that with wire, the quantum RF, and the ZAC, the inertial. They're all sort of leveraging and learning from the earlier product how to do these things better to make an overall better product. I'll stop there.
Thanks. All right, nobody's coming off mute, so I'm going to pick on Svenja. That's the next one.
Okay. So again, we have volumes that are around 1,000, 2,000 per year right now. Once you want to scale to much larger numbers, fabrication technologies really matter. For small companies, that's difficult, finding ways to kind of scale, because a lot of things are volume driven, and there's a certain, we can scale to a certain throughput, and then we need a new technology to scale further. So I think it's that scalability and developing as the market grows, these scalable methods of making things. The other thing is, like, every project I've worked on so far for the last 25 years, an atomic project always turns into a laser project. And it's still a laser project. And the laser is still an issue, and an issue of creating that supply chain that guarantees, supply of these components for while you're not at the point where I can just go buy wafers at a time. And so that's going to remain the same thing for us, and it has for a long time. But people are aware of it, and it is being addressed. But it's still hard to address. I've seen so many laser companies that get bought for some other reason because the quantum market just hasn't been big enough. So they get bought, and there goes your vendor again. I don't know how you can guarantee that a vendor stays, but I think maybe that's just my personal problem with these vapor cell ones, because we work with telecom lasers and they always have bigger markets. It's hard to sustain that quantum market yet, but as the quantum market grows, we need to make sure we can secure our supply chains.
And do you think that is a then like responsibility of the quantum sensor development to also, like, as you know, your various companies from all the panelists, to try to help that laser development, or are you kind of thinking of, we're waiting around for somebody?
No, I think that the laser problem is actively known, and there's certainly incentives to again build up companies that can do that. What's really hard is still to maintain those companies because and so I think what's important is that enough of the users get together to create enough demand that it makes sense for those companies to not just, I don't know, it's hard to compete with the optical mouse, right? Like because the sense our quantities are just not as high yet, but I think as our community grows, these quantities will get high enough and make it worthwhile. But it's hard to secure that while we're not quite there yet.
Yeah.
And so as users, I think we have to come together to start creating that need and that incentive. In addition to, there have been government incentives to solve that problem too. It's just hard to retain because you can't tell a company not to sell, and then shut it down again.
Do you think that has maybe one of the issues from this as like lasers is that there are so many different competing quantum technologies that all require slightly different lasers that we haven't as a community been able to get to that scale where we can have companies producing maybe that one laser output?
Yeah, exactly. We all need slightly different ones. Even I don't know, for the one for the Chipska clock was different from the one for the magnetometer. They were different enough that maybe you could marry it, but the market just wasn't big enough. And so I think creating that big enough market is good. Or ways that you can bring that technology in-house, that you at least control it somehow. Like, so maybe there's a foundry way that companies can get together and we actually build that up as one of the foundry technologies. I don't know.
Oh, those are all great points. Nick, would you like to?
Yeah, I think that is a critical challenge. It's like the P times Q problem, right? If like it's going to cost a fortune if you only have a small Q quantity, and I think the problem is you can't get to a big quantity if the price is too high, right? So we're in this kind of vicious cycle of trying to. So I think the organizations that are developing these technologies end up having to make some decisions on what part of the technology stack you can sort of drive and control to kind of make sure you can manage those costs, right? If you have to farm out sensor fabrication to a fab that's going to charge you, $100,000 a wafer run or something, right? It's going to be hard to compete, but then you have to build the capital to build those things yourself. And so I think there's challenges there. And I know QED-C had those reports about the laser inventory and things like that. And I think that just pointed out kind of the problem, which is this sort of starburst of use case of needs, and then trying to get to some consolidated set of requirements, or I think there's foundational technologies that might solve some of those requirements or multiples of those requirements. Because I think we're all under pressure. If we want to achieve adoption, we're going to all under pressure on swap C, and that means trying to get to that volume capability of the components. And the lasers, I think I agree 100% with Svenja there. The lasers are such a critical part of this system. The other part of it is, there's a fair bit of COTS stuff in there, FPGA boards or maybe custom ASICs that you then develop around that. So there's a fairly big supply chain of stuff that you can buy off the shelf, which is sort of volume. But those sort of critical things, in our sense, the vapor cells or the sensors themselves, and then I think the lasers and how those get integrated into the picture. I think those are some of the key things that need to be, pushed to really move this forward to a volume business. The other challenge, I just want to add one other thing. The other challenge is eventually break fix, right? So we're going into a world where today people buy electronics for a lot of these technologies, and now you're selling them or providing them something with all sorts of other, guts inside. And that's going to challenge, I think, the support and the break fix environment in the field of these technologies. So I think that's a challenge that needs to also be on the radar for people to overcome if we view mass adoption of these technologies over time.
Yeah, I think that's a great point. I mean, even for the FPGAs, but maybe that's one of the things that photonic integrated circuits could also lend to, is the fact of like, different quantum companies being able to design their PIC and design effectively their laser system from a large foundry, or like in the case of FPGAs, being able to get a board and then design software on it for your specific application or the ASICs. So hopefully in the next 5 to 10 years, we start seeing more of that and people being able to design their own lasers if we start to incorporate more gain materials into these processes. Elizabeth, would you like to have a comment on technical challenges?
Well, what I thought was funny is you said which ones are we closest to overcoming, and the entire panel was like, lasers are killing me. Well, I think William started us off on perhaps more accurate fit, but I think that points to the kind of the crux here is we're really closest to solving our challenges. We can make you a quantum sensor. What we cannot do is fix everything the quantum sensor needs. That is an industry-wide problem. So I think that's kind of uniquely indicative is the little bits that we control, we can do. We can always come up with a cool new material or a very fancy system, but whether or not it's useful. So I think the novel idea and the cool physics and can I make a system that will detect X, Y, or Z, I think that's what we're best at and what we can solve, just whether or not anyone can or will want to use it in the field I will not jump on the supply chain soapbox because it has been very well covered by previous panel members.
Let me add one comment there. This has been a great conversation, but I'm a big believer that this will be market driven, right? So as the market really opens up, as we get more sensors out there into the real world, as the sensors start to demonstrate their advantages, right, over existing or state of the art, that will create a demand signal, and industry will respond, right? And it's always been that way. It's been that with every single revolution that's taken place, technological, right? It's almost always been market driven. So I think if we just allow that to continue on, we will find there are going to be small companies out there that are going to specialize just in photonics, right? Photonic based lasers and frequency cones and things like that, that will feed into this growing industry of need, which is all driven by the market. So I think it will naturally resolve itself, which is very exciting. And to be, I guess, real frank about it, it is actually already happening right now. I mean, we've done things, there's a whole host of other companies that we're aware of that are focusing in on just the laser piece of it, right? On the PIC solutions. So it is happening. I would certainly say in 10 years, we're going to see very, very, good solutions that are going to emerge out of this healthy industry driven by a healthy market, right? That the way it should be done. So I'm an optimist. This is a very exciting time to be involved in this. And I don't think we need to overly control it. Just allow the market to do what it does best.
Thanks. Those are great points for it. Continuing on from what is the technical challenge we're closest to overcoming, now I want to go in the opposite direction and think about what are the biggest barriers, either technical or for adoption of this quantum sensing technology that you foresee, even as we're starting to see the technology is increasingly proven.
I wanted to preempt William just for fun.
Yeah.
Let you have all of them first.
Continue on, Elizabeth.
So I see a couple of them. One is just a general level of trust and inertia that exists with a lot of the intelligence community and the defense community. There are still planes with computers from the 70s, and we do not wish to upend, disrupt, or change them. Like, bringing in this level of change causes massive implications on accreditation, on validation, like just the time scale to bringing those things into security systems, into defensive systems is a huge challenge. And there's a lot of inertia of, I've got a thing and it's not broken. Don't give me something new that might be broken. So that's one of them. And the other, which I'm starting to see changing, which excites me with some of the DARPA programs that are coming out or work that we're doing at Leidos, or partnerships between companies like Infleqtion and the bigger sort of defense primes, is that for the longest time, quantum sensing has been in a box, guessing what we need, guessing what applications are important. And even beyond that, some of the most critical conversations are, can an RF engineer process what's coming out of an Infleqtion system? Do they know how to do the sensor fusion? Do they know how to interpret it? Do they know how to feed that into a military system or database in a way that it is processed and valuable in sort of the battle space? So there's all of these other questions down the line, which kind of goes back to, I think we can do the quantum part really well. Can we play with the engineers who need to use our data? Do we know exactly what problems we're designing for? And then, for goodness sakes, I'm so glad we have like the legal and standards tax. We have to start now talking to people about, this is what it's going to take to get one of these systems where you actually need it. And I'm being biased to government here, but even in sort of civil or health infrastructures, when people's lives are on the line, they're going to use, Sonia was talking about this, so they're going to use the machine they have that works. There's a lot of risk in jumping on that first adopter bandwagon. Finance has been really great about that for a lot of the quantum communications efforts. So those are some of my thoughts. I know starting over 25 years ago, certain government agencies were already looking into what is QKD and do we trust it? So the questions are being asked and poked at, and I think it behooves us as a community to really help show that we understand that, not complain that they're being tardy, and help that process move forward.
Yeah, those are all great points. For the biggest barriers, I want to jump to Svenja as somebody who is going now through FDA approval. See your opinions from going from the government space to now the health space, as what you see are the biggest barriers.
Yeah, so I think regulatory is actually not going to be our biggest barrier. It seems to be rather straightforward because there's a predicate for us. I think the two things is, one, these quantum sensors remain expensive. Even if we make them in very large quantities, we really want to, at the end, we want to bring it to everybody. There's applications where we want to bring it to the consumer market, and that's going to be really hard. So medical, defense can bear certain costs, consumer market cannot. So I think translating it to that is hard. The other thing I think that we need to be very careful with is the hype. Like, as we get these systems, we're starting to get these systems out, but people become impatient. And what we don't want is that there's so much hype that it's going to take a while to mature this, and they need to bear with us. And that I'm especially in that brain imaging field, we're really trying to control that hype and bring the realism. And I think in lots of quantum sensing areas, it's the same problem, because at the end, we don't want to fall into this valley of death because that hype collapses. People think it's already done. We're like, it's not done. It needs another 5 years to mature. Bear with us. And so that's what I would say.
Yes, I mean, I've even experienced the overhype of talking with people in the medical community who are thinking, oh, you can measure your heartbeat from across the room with these magnetic field sensors. And you're like, well, it's not exactly what is happening. We need to be close, but yeah.
You need to be close. You can't walk around. It doesn't work everywhere. We have to control interference. There's so many things we still have to overcome, but partially we as a society are creating that hype, and it's a dangerous thing, because we do need to bring that realism of what we can actually do and what we cannot do, and how long it's going to take for us to get there.
Yeah, those are all great points. William?
Yeah, great conversation. I think we're all going through the same thing right now. It's one thing when you work with early adopters. It's different when you get into the mainstream, where companies and government customers are a lot more, risk averse. And in some cases, you're pitching one of these technologies almost as a drop-in replacement in some cases for existing components and systems. And to Svenja's point, a lot of these are still very expensive, right? So you have this price disadvantage, right? You're not as price competitive as the existing technologies. They want it to be low risk. And what we have found that is very helpful is really changing our mindsets, kind of flipping the script. If you're talking to an early adopter, they're generally just really fascinated about the science, the physics of what's going on, right? And that's usually how you'll present the technology to them. And those are really the first questions that will come. But when you're in the early majority of customers that are looking for something that's more mature, that's much more practical, right? You got to flip the script, and you have to do your own due diligence to understand their needs, right? So if it's a government customer, what are the missions? What are the mission critical needs? And help through ideation come up with a way of addressing those problems, and show how that your technology or your product can become integrated as part of a larger system solution to address those. And then the conversation changes, because first you're addressing their needs, which they really want to hear about, right? And then naturally there will be questions about, well, show me that it's real, and you can take your technology out to their integration and test labs, to field events, begin showing them that it is actually real, that it's living up to the bare minimum requirement set that's key and critical to them. And then the third stage of it is that they eventually succumb to saying, well, now you got to tell me how it really works. I'm interested now in more of the science. We found that very effective, like flipping the script, understanding who your customer is, what their needs are, and working with them, right, to come up with solutions. And I'll say that in the process of doing this, one, you're educating them in a multitude of ways, and in particular, in helping them understand, and Nick was saying this earlier too, that the way you thought about solving these problems in the past has been limited, constrained by the classical technologies that you've been trained on, right? And it turns out that when you start to adopt some of these quantum sensing solutions, use these as a new tool set, those constraints go away, and you end up with different architectures, fundamentally different from what they previously conceived. And that's when the light comes on, and they start to realize, oh, I didn't realize I could do that I've got now not only enhanced performance, but there's whole entire suites of new capabilities that they can begin to realize. And then you got them hooked, right? Because now they start to imagine the future, right? They're thinking ahead about how I solve these bigger problems. And that for us has been a way in, and I think it's a way in for a lot of these companies. But that transition from being a research organization where you're used to talking about the physics, and then switching over now to a customer focused discussion around their needs and how you can address those needs. To me, that is exactly the next step you got to do to overcome the barriers, right? That's the risk aversion that the early majority has, that you can overcome that by just getting to a discussion about their needs and how you can solve them. So I'll stop there.
Thanks, Will. Those are great points. Nick?
Yeah, so I subscribe to the model. I think that there's not just one valley of death, there's three valleys of death. And I think if you look at that model that says, idea to prototype is the first valley, prototype to product is the second valley, and product to scale is the third. I think, if you look at those phases, and William was just touching on some of that, right? The first phase, that idea to prototype, that's really about the hard innovation work and getting the technology and figuring out how to make it work. That next phase is the prototype to product. And that's where you do have to do not technology work, but product work. Like, is this a product? What job does it do for somebody? What problem does it solve? And can you show them, and what's your value proposition and your support of that value proposition to say your product's better than anything else that you can buy to do that job today? And I think that's kind of where a lot of this technology is now. We kind of have prototypes. Now we're trying to figure out, do we have products? And then some of that conversation we had earlier was really about the scaling, fabrication, lasers, and things like that, right? So if you start to think of it in that way, and that's not mine, that's the Office of Strategic Capital. I love that chart, because I think it frames kind of where you are and the challenges that you're trying to face as you take this technology forward. We are in the phase of quantum needs product managers. We need people who can take technology, work with the market, and build products around these technologies. And I think that's that second phase. For the stuff that's working, is making it into products or solutions, as William talked about, that solves the problems that for specific end users, and has a market and a value proposition, and has an ROI statement that says, I'm better because ABC.
Can I jump on the back of that
Yes.
real quick, Nick? So we talk at great length about the workforce challenges that quantum fill in the blank anybody suffers trying to find good talent. And what you're discussing, Nick, is this critical inflection point that we have that I don't think a lot of us address, which is that's when your startup turns over half its staff, right? Or, your research lab loses half of its staff because the people who want to be constantly doing the cutting edge, the latest, the new design, they have zero interest in turning into product managers. And I think there's going to be a different sort of pipeline or technical staff challenge when you need someone with that deep technical knowledge, but the interest to really push it through to a product. I frequently get a lot of really great people on my team just because their particular corner of the quantum ecosystem hit first attempts at productization and they go, can't be bothered. So it'll be really interesting to watch how we try to adapt and what the workforce morphs into as that becomes more and more of a problem that we're facing.
Yeah, those are all great points. And, figuring out also, whether those product managers need to be detailed in the quantum physics behind it, or whether or not they just need to be product managers for the black box that they have. All right. Yes,
Can I
Will.
add to that? That's a great
Absolutely.
point. And we've all seen that. And hence, like, if you look at how we're growing, we're growing significantly in the engineering ranks, right? Because we have to bring in the engineers who know how to think about product, who know how to design your requirements into schedules when you got to meet dates and things like that. And so that is actually naturally happening. And it's sort of solving itself in that we're able to keep our physicists focused on doing research and using the spin outs from what they do, right, to feed into the product that's being developed. But we're seeing a lot more growth, and ownership of the product side by the engineering community within our organization. And so that is evolving in a very, I'd say, healthy way. So I can see, like, in organizations that are predominantly focused right now on just doing research, that's going to be a challenge they'll have. But the companies like ours that are moving into product, we're doing the right things. We're pulling in, tried true talent, proven talent from industry, folks that have been doing this for decades, right, to help us accelerate the actual product development and not have to, rely on the within our organization to do something they really don't want to do, right? And so it's a great point, and there are ways of remedying it, right, and being successful, and it's happening in companies.
Thanks, Will. And with that, I would like to thank all of our panelists for taking a time out of their day to participate in this great discussion. Before everybody leaves, we would like to run a short poll for the quantum marketplace. If you could stay and answer those few questions, it would be great for feedback for the quantum marketplace program and how it will continue. And I would also like to point our panelists, if you have a little bit of time, there are still 3 questions in our Q&A. If you have time or interest in those questions, please feel free to type out an answer. I'll stop sharing. And again, thank you so much for everybody who is in the webinar chat and our panelists for making this, I think, a really successful discussion about quantum sensors.